This video describes the new procedure added to Statgraphics 19 for fitting univariate mixture distributions. The data for the procedure consists of a single quantitative variable y. The model that's fit is a mixture or combination of two or more Gaussian distributions. As an example, I've loaded into the Statgraphics data sheet information on 272 eruptions of the Old Faithful Geyser in Yellowstone National Park. I'm particularly interested in the duration of the eruptions. To give you an idea of what the distribution of the duration looks like, I'm going to go to the top menu, choose Statlets, and select the interactive histogram. Duration has the data I'm interested in. And what you'll see is an interactive histogram with two definite peaks. Turns out, if you look at the eruptions of the Old Faithful Geyser, there are one set of eruptions that lasts between about 1.5 and 3 minutes, and another set of eruptions that lasts between 3.5 and 5 minutes. If I click on this checkbox, I can ask it to add a non-parametric density estimator. Non-parametric density estimator does essentially a smoothing of the histogram. And if I change the smoothing window a little bit, bring it down, you'll see two definite peaks in this bimodal distribution. The distribution I want to fit to this data is a mixture of two Gaussian distributions. The overall density function for the duration is alpha times one normal distribution plus 1 minus alpha times a second normal density function. Actually, alpha is the fraction of the observations that belong or come from that first density function. It's a value between 0 and 1. The other 1 minus alpha fraction come from a density function f2. In fitting this particular model, we need to estimate the mean and standard deviation of each of the two normal distributions, and also the fraction alpha of the observations that come from the first rather than the second density function. I'm now going to return to Statgraphics and have it fit that model to the data. I'll go to the top menu, select Describe, Distribution Fitting, Univariate Mixture Distributions. The indication R here notes that this particular estimation will be done by sending a script to the R programming language, having it do the fit, and then taking the results and displaying them in Statgraphics. If I push the univariate mixture distributions, a standard data dialog box will come up. I'll tell it the data to be fit is in duration. On the next analysis options dialog box, you need to specify the number of components. I'm assuming that there are two components in this mixture distribution. If I like, I could change options like the initialization method that will be used to determine the two modes before optimization is performed. I could also specify a random seed if I wanted to. I'll just go ahead and press OK. Now you'll see a list of tables and graphs that it will create for me. Again, I'm going to take the defaults. At this point, it will send the data to R, ask R to do the fit, and then display information in both tabular and graphical form. If you look at the table in the lower left, you can see the estimated parameters of the distribution. Approximately 35% of the observations come from the first density function. It has a mean of around 2 minutes, a standard deviation of 0.24 minutes. 65% of the observations come from the second distribution, the second component. It has a mean of about 4.3 minutes and a standard deviation of about 0.44. The fitted density function for the mixture distribution is shown here, and it seems to match the data quite well. If I'm wondering how many components I really need to properly represent this data, I can go to the Tables and Graphs dialog box and ask the program to do a model comparison for me. The model comparisons option will fit distributions with one component, two components, up to the maximum number of components I ask it to fit. It'll then show me the log likelihood, the Akaike information criteria, the Bayesian information criteria, and the classification likelihood criterion for each of the number of components. An interesting exercise is to go to the Analysis Options dialog box and increase the number of components to, say, 5. R will then fit distributions with one component, two components, three components, four components, and 5 components. The highlighted values in red indicate the best choice according to the different criteria. And here you can see the different criteria really don't tend to agree very well. Akaike information criterion says I should use 5 components. Bayesian information criterion says 3. The classification likelihood criterion says 2. Well, if you'd like to see what it looks like with 5 components, that definitely does seem to be over-modeling the data. Notice this little component here probably only has a couple observations. Let's back it off to 4. Go to Analysis Options, back it off to 4 components, which the AIC said was optimum. And now you can see the fit. And basically what it's probably picking up is some non-normality in the shape of the different components. Really, those 2 components that we fit for 4 are somewhat non-normal. By using 1, 2, 3, 4 components, it's able to match the shape of the actual data better than just using 2 Gaussian components.